Dear participants, let's now go forward with comparison instructions that are typically available with programmable logic controllers. You see, such type of comparisons are of absolute importance when you are deciding some output activation or disactivation while your input conditions are to be compared. Application demand might be like that. You have to compare the input condition with some constant parametric value, or you have to compare between the reading of two sensors that are connected at the input. So that's why proper application of comparison instruction can give tremendous versatility to the program. We have already seen about these compare instructions during our discussion with multiplication instruction, where we had compared the temperature sensor value with the higher trip point and lower trip point for the oven. So in this section, we will be concentrating more on these comparison instructions. You see that we will be having basic comparison function, application of comparison function. I have given you the idea. Now it remains an assignment for you to think of some situation where the comparison instruction or comparison function could be applied, and that you have to give an assignment. Finally, we will be talking about one or two advanced comparison functions. Now see that all such compare instructions or comparison instructions, they are simply input instruction. They compare numerical values, and the values have to be stored in two registers. Okay, so that the decision can be taken by comparing the value that is stored in these two registers. So that means that directly you cannot compare the value between two external sensors. You have to store their data in some register, and then only the comparison operation can be performed. Now you see that there can be several basic types of comparison. One can be equal to, then not equal to, less than, greater than, less than or equal to, and greater than or equal to. These are the basic operations. Now you see that when we had studied about event timer and counters, we had talked about this comparison. However, we had not gone into detail. Okay, so you see that whenever this timer or counter acts, you can find that when the accumulated value is equal to the preset value, because you can well remember that we have to give some preset value and then the accumulator keeps on updating both in timer and counter. So you could find at such situation that whenever the accumulated value is achieved, the timer used to either turn on or off. Now why this happened? This happened because the processor keeps on continuously comparing whatever the data is there in one of the registers, that is accumulator, and in the other register, that is the preset register. So whenever the processor finds that both values are equal, yes, it takes the decision. Now you see, comparison instructions are extensively used in order to compare pair of values. And finally, according to this comparison result, the condition of a rung is updated. Either it goes true or it goes false. Now you can see this RS Logic software. This is the comparison block, and you can have limit, MEQ, EQU, NEQ, LES, GRT, LEQ, GEQ, all these things are there. Greater if equal, lesser, lesser if equal, greater, then limit function, all these things are there. Let us go into the details one by one. Now initially we will have a quick look on this summary sheet of the compare instructions. You see, first of all, there is limit test, which is signified by lim. It tests whether one value is within the limit range of two other values. So here, this gives you the competency to work within a range of two different values. Okay, so that helps you to check whether your data is lying between an upper extreme and one lower extreme. Next, we have got MEQ instruction, that is masked comparison for equal. This is a bit complex. Okay, here you can find that it does not test the entire value. It does not compare the entire value. It tests actually portions of two values. Alright, you see, it compares 16-bit data of a source address to 16-bit data at a reference address, however through a mask. So wherever there is a mask, those bits will not be considered. So we will see the illustration definitely. Next comes equal. I don't think that needs any further discussion. Not equal. Then comes less than. Now you see, it tests whether one value is less than a second value or it is greater than a second value. So such type of comparison blocks you have also, I think you have definitely at any point of time you have prepared with op-amps. Okay. Then you have got less than or equal or greater than or equal. So this is all about the different comparison instructions that are available with PLCs. Let's first start with a very basic one, equal, EQU instruction. Now you see here, as we are already very familiar with, there are two data, rather two sources I must say, that contains this data, that is source A and source B. Here these two are compared. So what is the first source? It is the accumulator of timer T40 and the second source is N740. So if both of them are equal, then this lamp will go on. That means this rung will be true and this coil will be activated. Now you see that this source A, it may be a word address or a floating point address. Floating point address means you can go with decimal points, decimal data. Now we see with equal instruction, the floating point data is not recommended because of the exactness that is required. So floating point data is critical to handle because you know, after points, right, after point, the exact value, if it is not proper, especially because you see, if you keep a constant value and you need a sensor, then there is always a fluctuation after this decimal. So it becomes very hard to determine whether they are equal or not. Therefore, normally this floating point data is avoided in case of equal instructions. Next, remember that in all input comparison instructions, this is one rule of thumb, the source A must be an address. You can see here source A is an address. Now source B can be a constant value or it can be an address. So this particular constraint you have to remember. If you are trying to compare in between two constant values, you will not get any result. You will come with error. Next comes not equal instruction. So when source A is not equal to source B, the instruction is logically true and your rung gets activated. Your lamp is on. Next comes greater than instruction. Okay, you see this greater than instruction compares A with B. When A is larger, remember, when A is larger, so therefore A is the main thing that has to be compared with some constant value or some register that is containing some value. This A has to be measured, that you remember. Next comes the less than instruction. I don't think that we need to discuss a lot on this. Then comes greater than and equal to, less than and equal to. Now you see, finally, I will come to some instruction that is interesting. There is one problem with this. You see that say less than or equal. Okay, I think that I have not changed this. Okay, that is a copy paste problem. I'm extremely sorry. I will go for this limit test. Okay, this is lim instruction. LIM. All right. Uh, okay. Now let's concentrate on the limit test, that is lim instruction. All right. Let us see here. This is a special instruction as I had already told. The limit instruction is used to test whether some value that is within or outside a given specified range. Now you see that during the discussion of our multiplication instruction, we had to compare the sensor value in two occasions, one in case of the upper extreme and one in case of the lower extreme. If we consider the limit test instruction, then it is possible with one block instruction only. We need to go for two separate comparisons. Now you see, now by now you can easily consider that while using this LIM block, definitely there will be three parameters that we have to feed. One is the low limit value, another is the high limit value, and finally there should be the test value, that is the input. Now you see the limit test instruction, actually they have got a dual way of functioning. I will be discussing one by one. You see here the instruction can be true if the lower limit is equal to or less than the higher limit and the test parameter value is equal to or inside the limits. Now you see the lower limit is equal to or less than the higher limit and the test parameter is inside the limit. What does that mean? That means that suppose your higher limit is 100, lower limit is 95 and the measurand or the parameter value is 96 or 97. then it is true, otherwise it is false. If the value, if your measurement is maybe that parameter value is 110 or it is 90, it is false. Next, another condition: the lower limit has a value greater than the higher limit. Lower limit has a value greater than the higher limit, and the instruction is equal to or outside the limits. Now you see, the lower limit has got a value greater than the higher limit, and this instruction is outside the limit. That means it is not within the limit. Okay, we will see the illustration. You can see the first condition. The low limit is 25, the high limit is 50. You can see here very easily on this number scale, this is 25 and this is 50. So if your test value, that is the parameter value, is less than 25, the condition will be false. If it is greater than 50, the condition will be false, and any value in between this range of 25 to 50, the output will be, the run condition will be true and your output will be energized. Now let us look into the other condition. You can see here that the low limit is 100. You can find the low limit is 100 and the high limit is 50. Are you getting my point? Here the low limit is 100 and high limit is 50. Now, what is the test value here? 125. You consider the situation. At what condition this rung will be true? When it is lesser than 50. When it is lesser than 50. That's why it is called as high limit. Or when this 100, it is more than the parameter value, then it will be true. Then it will be true. Okay. So you see here, just a minute. So you can find that if the parameter value is lesser than 50 or if the parameter value is greater than 100, then only it is true. In that sense, this 50 is a high limit because it should not be greater than 50, or it can be on the high limit side, this low limit side, or it can be greater than 100. So this is true. You can see in this case, this is true within the range. This is true outside the range. So limit instruction can be used in both cases. Now you see, the limit instruction is said to be circular because it can work in either two ways that we have just seen. Okay. Again, there is this problem. So while I had prepared this lecture, I think I was not much attentive. So you see here, this is one important concept, that this limit test instruction is always a circular instruction because it can function in both the ways, as we had already seen. Next comes masked comparison for equal instruction. This is also known as MEQ. You see, this is a very special instruction and we need to understand it well. So you see here, this is the MEQ instruction block where you have a source data, and here you have to compare with the data that is supposed to be against this compare variable. So this source that contains one data and this compare that contains the other data. In between there is a mask. Now you see that when the data at the source address match the data at the compare address, so this is the address. In each case you can find there are addresses. Okay, bit by bit the instruction is true. So this MUQ instruction that compares the data bit by bit. So this is compared. This 0, 0, they are same, 1, 1, they are same, 0, 0, they are same, like that. It compares bit by bit. So the data that is at source and the data that is at compare. So these are these, whenever you invite this MEQ block, this source, mask and compare, they will be inside, written inside the block by default. These thing are the variables n75, n76 or n710. These are the variables that you can put. Okay, and inside these registers you can put your data. Now you see that while reading this statement I had missed one thing, less masked bit. So you see that instruction is going to be true when each and every bit of the source data is exactly identical to each and every bit of the compare data, less the masked bits. Now you see the particularity of this mask. Whenever this mask is containing 1, this mask is containing 1, that means those data of source and compare that corresponds to bit that is 1 for the mask will be compared. So here you can see this 1 1 1 1, wherever there is a 1 in the mask, the data will be compared. But where there will be a 0, this data will not be compared. And remember one important thing, that the mask must be the same element size. So if this is a 16-bit data as the source, 16-bit data at the compare, then the mask should also be 16-bit long. Do not commit a mistake here. Okay. Now you see that where you want to compare the data, you have to set the mask bits to 1, or you have to write 1 to the mask bits. And where you do not want to compare the data, you have to write 0. Okay. So if your ladder program, this is one important concept, if you want the ladder program to change the mask value, store the mask at a data address. Store the mask at a data address. Otherwise what will happen? Otherwise you can go for an hexadecimal value for a constant mask value. So whatever your mask value is, you have to write an equivalent hexadecimal value. Alright. Now you see in this case, this output is true. Why? Because at the 0000 condition we have not checked it, and for all condition of the mask where it is 1, the source and the compare, the bits are exactly the same. That's why the output is activated. Alright. So you see here that you need to identify one data address where you can store the mask, and you can call that data address whenever this mask has to be called for this MEQ operation. And if you similarly, if you want to change the mask, you can go directly to the data address to change the mask according to the necessity of the program. Now let us go for one application. You can see, suppose there are 16 limit switches. There are 16 limit switches and you want a particular, I should say, pattern of the activation or limit switches. You can see here what we will do, we will store their desired state. Might be the desired state can be 1001 like that. We will put that in compare statement, and then we will accordingly mask to know which switch has to be on and which switch has to be off in order to get a particular rung true. Suppose, let us just take for an example, there are 4 limit switches, and in order to get a rung true, the first switch should be on, second switch should be off, third switch should be on, and the fourth switch should be off. If you want to see whether this is correct or not, then in the compare, you write down this data 1 0 1 0. Then you compare it with the source. You have to compare all the bits. So in the mask, you will be keeping 1 1 1 1. Then compare. So whenever the source is 1 0 1 0, then only your output will be true. So that is masked comparison instruction. You see that I am talking all these things only from theoretical perspective. In your lab sessions, you will have to perform all these aspects apart from the experiments that are already given in your syllabus, lab course syllabus. So those are only part to be completed as a part of the syllabus. However, you need to comply with all these statements from your own confidence. Yes, I can do, and I believe that yes, it is happening. So that is what I require as assignment from your side to be performed. I hope we will be doing this once you are here. Thank you.